So yeah, welcome back, and yeah, I think we should actually start with the first lecture. It's all about computational thinking. So it's about thinking like a computer scientist, speaking like a computer scientist, and also solving problems like a computer scientist. Well, computer science, it's not only programming, it's facing problems. So yeah, we can say from experience, you will face a lot of problems during your studies, most of them computer science related, and you then have to think about strategies how you could solve all these problems. There are different strategies to solve a problem, but you have to find a particular way to solve them.
Before that, sorry to interrupt you, but before that, I just saw the one question in the chat about Design Your Own App and ESP now. So we know that also for learning C course in Design Your Own App, the dates are now here when our lecture is. So I just want to give you a short overview how this works now before we dive into the topic. In Design Your Own App, in this Learning C part, it is mandatory to attend, or not to attend, but it is mandatory to do ESP and then do this additional ESP course or this Learning C part of Design Your Own App. So the only thing why in Design Your Own App the lecture is now is because you should watch the ESP lectures, but most of you, maybe many, or maybe all of you, anyway do the ESP lectures. So the good thing about that is you can save, for example, time by just attending the ESP lecture, and in the end you do the additional part or the additional assignment, and you will get the ECDS for Design Your Own App. So when you don't have to be here, it's just in both lectures, it's in Design Your Own App and in ESP, the lecture now, the date now, and the time now. So yeah, you don't have to be here, but you can access it. And the idea is that you get the C knowledge and you maybe attend the ESP lectures if you want this Learning C part.
Yeah, thank you for that. That's a very important remark. So to clarify this. And yeah, to come back to the computational thinking lecture, you as a computer scientist will acquire a set of skills. And one of these skills will be the problem solving skill. And most likely throughout your studies and also your professional life, the majority of problems you will face are technical problems. So you also have to find technical solutions to solve these problems. And there are different techniques and strategies to solve problems. For example, we have a short, real-world example here. Let's assume we move to a new place and we want to reorganize 150 books. So I live in a small apartment, I have 150 books. It's actually a mess, and now...
It should be a mess, because 150 books in a small apartment is a lot.
Quite a lot, yeah, that's true. And now I move to a larger apartment, I have more space for my books, maybe, and I also want to reorganize them to quickly find what I need and what I'm interested in at the moment. So what do you do? Let's assume we have this set of books here. What can you identify in this set of books? Just drop in the chat what do you think about. So what can you identify when you see this image?
Any ideas in the chat?
Yeah. Organized by name or by color. Yeah, that's color. Yeah. So yeah, in this image, it looks like it's somehow organized by color. That's true. Orientation, size. Yeah, chaos, that's true. It's really a mess here. Alphabetical, stacked. Yeah. Okay. So, what have you seen? You have seen quite a mess, that's true. Quite a lot of books, and actually, it's maybe organized by color, but we cannot 100% for sure say that. So, we need to extract some information from the books. What do you think are or is relevant information if we want to reorganize these books? Just some features, some properties of a book. We have already seen a title. Yeah? That's yeah, maybe quite important feature of a book. Name, author, genre, topic, yeah, that's really good. Content, number of pages, yeah. Context, maybe the date also important, so when it was published. Exactly, so yeah, it was mentioned multiple times in the chat, the author may be relevant information for reorganizing books.
Frequency of usage is interesting because
Yeah,
it makes sense to have the books which I often access maybe closer to my desk than others.
Yeah. So yeah, popularity definitely an information that could be relevant for reorganizing. We also have some interesting information. It's the ISBN. Do you think that could be a relevant information, or would you reorganize the books based on the ISBN? So it's the identification number for books. Would you do that?
If I would suggest that Monk will do it, but
Yeah, okay.
I'm not that guy.
Yeah. So I'm not really sure if anyone would reorganize their books by ISBN. So yeah, but it's definitely also a feature. So an information of a book. What else do we have? We have the publisher. We have the publisher, we have the publication date. So that could be also a way to reorganize the books. Yeah, that's, I would say, quite a
lot of information, yeah.
Yeah, a good set of information. And if we now continue, what do you think? Are there any relevant patterns in the books?
So what do you mean with pattern?
For example, we have heard the number of pages, so maybe the thickness of a book. Page count, yeah. For example, length. That's also quite interesting. Soft or hardcover.
Okay, yeah.
That's, yeah. Yeah, we've heard it multiple times. The size of the book. What else can you think of? Topic is also very good suggestion. Language, yeah. Chapters. We have the color. So if we recall the image we've shown before, so the color might be also a pattern we have recognized. Maybe it's not the best way to reorganize the books, but yeah, it is a pattern. Yeah, we have the genre, we have the topic, so the category of a book. And all of these are patterns we can extract from the books we have in our apartment, the 150 books. And with this information, we can now go a step further and could reorganize the books. So the next question is, how can we actually organize the shelf on which the books will be placed on? So how can we then group these books? ABC, so alphabetical. Alphabetical, yeah, very good.
Interesting. Would you really do it alphabetically? Maybe in a library, yes.
Yeah,
But even then, even there in the library, it's most likely not alphabetically.
so with alphabetically you mean by title?
By title,
title,
yeah.
Okay. Maybe it makes sense by author.
Yeah. But when I go into library,
Yeah.
of course every day, I have another sort of organization there, I think. Yeah, I think it's the genre, right?
It's the genre.
It's the genre, yeah.
Category, yeah. And so this could be one overall reorganization approach. Maybe within genres there could be another approach. What do you think? Frequent usage, author name? Yeah, we could, for example, also then group them by the author. So there's no false answer here, so it's just getting ideas how we could organize the shelf. Yes, exactly. We can, of course, also use the colors again. You can just organize the shelf using colors.
Would love that library that has the books based on the colors and grouped by the colors. Would be very interesting to find a book there, but
I wouldn't find anything, to be honest. Yeah, and what we've also mentioned before, the popularity. So I haven't been to the library quite in a time, to be honest, but as I can remember, if you go into the library, there are popular books.
There's most likely a section, one bookshelf with the most popular currently, yes.
So this might be a good approach for at least a subset of all books we have. Okay, so now we have different approaches or strategies to organize the books. Now we want to find a strategy, or we want to find multiple strategies actually to find the books efficiently. So what do you think could be a suitable approach for finding the books in the shelf? So just describe it in the chat, use just a natural language. We don't need any algorithms yet. So we have now a shelf, and these shelves are the books, and we want to find one specific book in the shelf, so in the set of books. So
is the shelf already sorted? Yeah, we don't know. Hopefully.
We hope, yeah.
We hope, yeah, but we don't know if the book is already sorted.
So let's assume it's alphabetically sorted. And we now want to find one specific book. How would you approach this? Yeah, when you look at its cover, we already have algorithms in the chat.
Yeah, we'll come to the algorithms later on.
I see you do it in a phone book. That's quite interesting.
Okay.
QR code. Yeah, go to the first letter and then read through the titles. Yeah. So if we now have a look, one possible strategy is to order the groups by title, order the groups by author, and also by popularity. But also we can also again order it by color. So if we define a specific order, we could also order it by color. So it's just about extracting information and in this specific context then finding a strategy to solve the problem, so to find a book in the shelf efficiently. And maybe now you ask yourself, how does this help in computer science?
And if you are not happy with the answer we provided now, we do it on purpose. Yeah, so of course we do not provide now algorithms. But we just want to give you an example of a problem in computer science, for example, and you can now solve it. Maybe not now, but we learn to solve a problem like this in the next few weeks. Yeah, but how can we do this in computer science?
Yeah, it's really thinking like a computer. So you have some, in this case, a real world object, a physical object. You extract information from this object, or in this case, 150 books. And we have now identified some relevant information. It's the book title, it's the publisher, it's the author, and so on. And you will then, in your computer science study or professional life, face similar problems, which you have then to solve using some kind of programming language or any computer science related technique. And this was just a real world example, which is not really related to computer science, but you have to learn the strategy to solve this problem, because you will face it definitely throughout your studies and after that in your professional life.
Yes. And we have another example where you already faced like this computer science problem. I hope most of you, or I would say most of you, already used something like this. This is a simple vending machine for drinks. I don't know what's in there, fruits, food, whatever. And what we now want to do is we want to, think of how this can work. So of course there's not a person inside who interacts with us when we want to have a drink out of it. There is a small computer program, and we want to now infer how this works under the hood. So in this case, we have this simple vending machine, and it has very basic properties. It waits for coins. You can select a payment. You can pay with cash or with card. Then it processes the payment, and then it gives you the drink in this case. And what we can do now is we can create a chart where this process is stated. So we start, I hope you can read this. Yeah, should work. You start, and in the beginning, the vending machine gives you a welcome message. In this case, it just says welcome. And then the next step, what the vending machine does is it sets the current input to 0, 0.0. So it means there are no euro, no cents inside. You have to put an amount inside to get the drinks. So the current amount of coins is 0.
Yeah, that's exactly what I wanted to ask you. I don't have any coins with me. Could I maybe also use some kind of card?
Yeah. The next phase, you can select the payment. So the display says, okay, please select the payment type. And you can choose between card or cash. Okay, you want to have card, I'll do it with cash. So when you are on the card branch on the left, you can insert the card. There's maybe a card reader and you can tap the card there. Or when you have cash, take the coin and input it into the machine. When we have cash, in this case, when you imported a coin, it gets added to the current input. So let's say I want to buy a drink, which is €1, and I input €1, so I give one coin inside. Then I have the correct amount and hopefully get the drink. So if the input is higher or equal than the price of the drink, then it should work. And if not, then it should not work. That's the basic principle of the machine. And on the other hand, if the card payment was successful, you should get the drink. If not, you should not get the drink. So you have here again like a decision to make. Was the payment successful? If not, go back and select another payment method. Was the price, or was the coins you entered higher or equal the price of the product? If not, go back again. And if yes in both cases, then give the drink. Are there any problems with this vending machine? Do you spot any problems here? Because I would not go there and take a drink from it. It's a bit risky in my opinion. But do you spot any problems with this simple chart here, with this execution paths? Yeah, no coins return, for example. Yeah, so if I give too much, it won't work. Even if I give too less, it just say, okay, if input is higher, even if I get too less, I will always go back to this no part. So the problem is I have to give the exact amount. So let's say we have, I don't know, €1.20. I just can input here maybe 1 coin, so I will never get to this amount. I will never be able to pay with cash here. That's a very, very bad program behavior then, and I don't want that. So this is very, very easy example, but believe me, there are such very, very easy problems out there. There are vending machines which have, for example, this behavior where you maybe do not get a cash return, or it's maybe impossible to pay a specific drink because you don't get to this amount exactly.
Yeah, also a quite interesting comment in the chat was there's no possibility to cancel an order.
Yeah, that would be also a very, very good idea to cancel. Maybe I want my cash back. Maybe I found out I don't have enough coins. I want to switch to card. Yeah, so as I said, this is not the vending machine I want to buy drinks from. Yeah, in the end, I forgot about that, but in the end it says thank you, and it would be great then to start from the beginning again afterwards. So in this case, it's only possible to pay 1 drink and then the vending machine stops. It's also not a good idea. Maybe we would miss here a branch going out again to the welcome message to start once again. Yeah, we also discussed that how you could improve this machine, because there's a lot of problems in this machine here. So what I showed you now was a so-called flow chart, and I just want to give you a short input about that. It is a representation of a workflow, in this case a representation of a program, of some source code written by a developer, and you can always represent source code in this flowchart diagram. There are different types. There are processes, conditions, in and output, and terminal. Or terminal in this case is just printing something to the user. When we go back, you can see this here is a decision to make. So this is a condition, yes or no, maybe. This here is also a condition. If no, go this part. If yes, go this part. In this case, it's not yes and no. It is select card or cash. But when you have this rectangle here, it always means there is a decision to make. This is always a process, for example. And this is then an input, so you have to give something to the machine.
Just one question here. So would it be possible to have another payment type I could select? Would this be possible, or?
In this case, it depends on the flowchart diagram. In this case, not, but you have to select another type here, and then you can have multiple options.
But it would be possible to have.
It would be possible in general, yeah, of course.
That's cool. Yeah.
But it depends on how I create my program.
Yeah, of course. Yeah.
But many computer programs, especially when they are hard to think algorithms, so very hard to understand algorithms, it's a nice idea first to create a flowchart to get an idea of what you have to think about, and then it's much easier to program it. It's not necessary to do in our lecture, but sometimes if you have a very, very hard to understand algorithm, it helps a lot to visualize it and which paths do you know and you have to do. All right, Any questions from the chat there about that? The money doesn't reset. Yes, my money is gone when I answer this. Unfortunately, yes. Yeah.
But we've just said, so can I write a flowchart and take that with me to the practical interview for assignments?
You can do, yeah, of course. If it helps you, yes. I would argue that the flowchart can be quite complicated for the assignments, and I would not recommend to write the whole assignment as flowchart. But if you have a specific part which is hard to understand, you definitely can do it. There are lectures later on, I think in the 4th and 5th semester, where your actual task is to create such a chart from your source code. Or the other way around, create source code from a chart. So you will practice this later on.
Yeah, it's quite beneficial and also deepens your understanding in both ways. Yeah.
Yeah. All right.
Okay, then let's continue with the computational thinking. So computational thinking comprises a different set of skills. The 4 skills we will talk about today is abstraction. So we have already touched it with the bookshelf example. So to find the relevant information of, for example, a physical real-world object. Another important skill is the decomposition. Let's assume, again, we have a messy room and we want to clean the room. How would you approach to clean the room? So we have to vacuum it, we have to clean the desk, and so on. What is your approach of cleaning a room? Divide into smaller tasks. Yeah, that's already really good. Highest place and go lower. Yeah, that's maybe
highest place and go lower. That's a very good idea, because otherwise you have problems. Yeah.
Maybe it's also just a bit related to algorithmic thinking.
Yeah, it is.
Yeah.
So you might see that you already used some algorithms in your daily life, but didn't know it.
Yeah. In flow at the end, makes sense. Stick to one task at a time. Yeah, that makes absolutely sense. So maybe you should first put your clothes to somewhere else, and start from the highest area in your room and then go lower. So you really divide your tasks, for example, putting clothes to somewhere else, then cleaning your desk, for example, and at the end vacuum your room, the rest of the room. So it's really dividing and conquering, for example, which also is required in programming, because you cannot solve a big problem at once. You have to find some sub-solutions and strategies to solve the sub-problems. Yeah, and it's already related to that, algorithmic thinking, to find a procedure, to find some step-by-step solution to solve the problem. David has prepared a really nice example for that.
We will come to that.
Yeah, just as a teaser.
Also the other tasks, so maybe we should start with abstraction, with the first one.
Yeah, so you can see here quite beautiful image of an elderly person. And how would you draw this in an abstracted version?
So what is abstraction in general?
It's really just focusing on the relevant information. In this example here, it's a person. So we agree this is a person. How would you draw it by just describing that this image shows a person?
Yeah, so I will do something like this.
Oh, looks like it's drawn by me. Yeah. Is it my drawing? I think.
It's a human being.
Yeah, exactly.
Yeah.
It's a human being. Yeah, stickman, exactly. 5 lines and a circle, yeah. Yeah, it's dropped in the chat, so Beard would maybe be relevant, but if you just want to tell another person that a person is illustrated in the image, such a stickman would be definitely enough. So this is just abstraction for a person. How would you now simplify, so find an abstract version of a highly complex system like a computer? So how would you simplify a computer? What are the most essential parts, components, subsystems of a computer? Maybe some suggestions in the chat. Yeah, processor processing unit, that's
Yeah,
quite
we
important.
know we haven't taught you this, and maybe on the 3rd of October no other lecture, so you don't have to know it, but
Yeah,
maybe you know some components.
yeah, you will get to know them.
Yeah. And I can read a few of them, yeah, many of them. So the most basic representation of any computer is always CPU.
Exactly, yeah.
Then you have some kind of memory, short-term memory, also called RAM, all the time, most of the time. And then you have like, oh, it's in German. Just realized it's in and output.
Yeah.
We have the disk, so the Festplatte in German, network connection and the keyboard, for example. But it's basically the same as this, but
just
in an abstracted way.
Exactly, on a very high level, simplified way. So this actually has a name, the abstraction of a computer. It's the von Neumann architecture. So its heart is the central processing unit, the CPU, and as David mentioned, the other components are a very, very simplified version of a computer. But if you show this abstraction to a person that is somehow related to computer science, they will know that this is an abstraction of a computer.
And maybe includes more information than this.
Exactly, yeah.
Because, yeah, you can see here the CPU, the memory, and so on. Okay, let's go on with abstraction. There are other ways or other types of abstraction in maybe our daily life.
Yeah, there are. So maps are a brilliant example for different abstractions based on the same object. In this case, we have Austria as the object on a map, and we have here the political map. Don't be confused, political in this sense is not related to politics. So even though we had an election last weekend, but it's not related to politics. It's more about administrative relationships, conditions, and exactly.
And let's not get political.
Yeah. Let's skip that. Please just add in the chat what you see here, or why do we need a political map of Austria? So we have already Bundesländer here. Yeah, exactly. So we have, let's call it states. What else can you see?
Federations, yes. Yes, Südtirol.
Large cities. That's very, very good. Be honest. Here there are the most important roads, rivers. Exactly. Bundesländer, Hauptstädte, Flüsse.
But is this now the exact representation of Austria? So is this basically Austria?
In some kind, yes. So in a specific context it is, but of course it's not a real representation of Austria. It's just for one specific, or in one specific context, it is useful to have this abstraction of Austria. But, so let's assume we are people from outside Austria and we want to go on a hike, we want to go on a mountain tour. And so we want to visit a region in Austria that has at least, some mountains. For that, we will probably use a physical map, which illustrates where are the mountains in Austria, there are no mountains in Austria. And yeah, as you mentioned in the chat, absolutely correct, the darker the higher. So we will use a physical map instead of a political map to choose the location for a hike. And what is also important when, for example, planning a mountain tour, you have to look at the weather forecast. And for this, we will use again another abstraction, another representation of a map of Austria. So a weather forecast map is, yeah, the thing to go if we plan a mountain tour. And so we have now seen 3 different abstractions of a map of Austria. But if we shortly show them again, what do you see and what do you think are the features that all of these maps share? The borders of Austria, exactly. What else? Rivers? Yes,
Yeah,
exactly.
interesting, yeah.
Cities. Yeah, exactly. So it's mainly about cities, rivers, a country border, the shape of Austria. Yeah, exactly. So to quote something, abstraction is the process of simplifying and hiding detail to get at the essence of something of interest, which means we leave out something that is not interesting for us to get the information that is interesting for us, for a specific context. And that's what abstraction is actually about. Yeah. And how we can now use such an abstraction. One example is data abstraction. So think about a person and think about what data is related to every single person.
Or let's say of a student in a student management system. Yeah.
Exactly, yeah. Let's say student. What data is related to a student?
Birth, yeah.
Name, age.
Hopefully every student has a birth. An age, yes.
Email, yeah.
The liver is interesting, yeah. Hopefully every student still has one.
Yeah, we have it multiple times here, the Matrikelnummer, the student ID.
Yeah.
That's definitely important. Nationality.
Studiengang, yeah. Field of study. Makes sense, yeah.
Yeah, very good. And what do you think now is really the relevant information for building a student management system? So we want to build a system where all the students are represented with the at least most important information, so the most important data of a student. What do you need?
Do I need to know if the liver, for example, or I don't know.
I'm not sure if there is any university in the
I don't know.
world, but at least here in Graz, it's not required, as I know. So
you need to know, of course, the student ID, the name would be good.
Yeah.
Also the birthday.
Yeah.
The field of study, very important, because as university you have to know what the student is studying. And this is, basically I would say the most important one. Of course, maybe an address.
The nationality,
Nationality, address, would be good.
Plagiarism history,
This is also stored somewhere.
Yeah, it is definitely stored, Okay, but that's really good. So we now extracted the relevant information and split the relevant information from the non-relevant information of data. That's very good. And another strategy we can use is the divide and conquer strategy. So it's the Teile und Herrsche approach. For that, we have prepared a, I would say, quite fun example. It's Super Mario. So I hope many of you know this and maybe also have played Super Mario. And
I don't know. Is it still a thing? So it was maybe in our times, and
yeah,
we are not old, but we're not the youngest, maybe. Yeah. So I still can remember playing this.
but it's still a quite cool game, to be honest.
Yeah.
So
And it's very self-explainable
Yeah,
when watching
yeah.
this. Yeah.
exactly.
But this is already, so it seems very simple compared to the games currently playing or currently
Yeah.
available. But it also has already many different characters and many different types inside.
Yeah.
So it's hard, even for us maybe, to build a game like this. We can do it, but there are so many different things we have to think about.
Yeah, you're absolutely right. It's really not that trivial as it looks like, maybe. So if we now decompose Super Mario, we have different game elements. So we can categorize them. We have elements we can play with. We have elements that are static. We have elements we can interact with. Again, other are non-interactive. Some are useful. We can collect coins. We can level up, but some are maybe disadvantageous. And if we now decompose Super Mario, we want to build some elements or some higher level elements which share some common information or some common characteristics. Which means we have, for example, Super Mario or the variations of Super Mario as a playable avatar. We have flowers which can be power-ups, which you can interact with them. With enemies, for example, Goomba, it's disadvantageous. And we also have the map as one element, but we could divide it into a interactable part of the map and a non-interactable part of the map. So those of you who have played Super Mario probably know that the pipe is interactable and other things are non-interactable.
Yeah, it's like the background.
Exactly.
Yeah.
Background, it's there, but it's not non-interactable. But still, it's there, yeah. And we also have some collectible items, so they're, again, interactable, but they don't have any other purpose than, for example, just collecting them. And if we now want to play Super Mario, what do you think are the functionalities that we need? So what should Super Mario be capable of doing? Yeah, movement. Movement is a very good suggestion. Jump.
Jump? Interesting. Is jump the same as movement?
We will see that in a few minutes. It depends, but we could say that jump is some kind of movement, yes. Crouch, yeah. Interaction, yeah, interaction is also a good suggestion.
Exist, yeah, it should exist. That's a basic functionality.
Yeah. Yeah. Interaction, taking up items. I haven't seen a Super Mario that can do a backflip. Have you?
No,
Okay.
never saw that.
But it would be cool. Yeah, so we have the movement functionality. So let's assume it's just a two-dimensional game. We can move in the X and Y axis. We have some collectible items, some interactable items, for example, coins. What's also important is the collision check. This is very important also for game design and development. If you there's a difference if you jump on an object or if you run directly into an object. So for example, there's Goomba. If you jump on it, it disappears. And if you run into it, it's bad. And of course, at the end, you also want to check if the goal is reached. So these are not all, but I would say the most important functionalities for Super Mario. And if we now want to create a move function by ourselves, what do we need? So let's assume it's two-dimensional. So in how many directions can Mario then move? Left, right.
Left, right. Yeah. Is there gravity? That's interesting. Yeah. So you maybe if you have 4 directions, so you can jump. You have to implement gravity
Yeah.
some kind, because otherwise it's jump to infinity.
Yeah, that's actually a very good point. Yeah, gravity. Up, down, left, right. Very good. Yeah, so we need those 4 directions. 2 directions in the x-axis and 2 directions in the y-axis.
Is there a way for Mario to go down?
Through a pipe, as
yeah.
far as I know,
Yeah.
there is, but...
Okay. But you do have to
you mean
press
crouch?
down? Or is it just falling down?
Yeah.
I don't know.
I'm
Can't
also not
remember.
sure about that. But I'm also not sure about it if you can crouch. So if you can
He
just
can duck.
dodge.
Yeah, he can duck.
Yeah,
Yeah,
you
yeah,
can?
makes sense. Yeah.
So yeah, we have these 4 directions. And now this is how we decompose Super Mario. We have different elements, and for one of these elements, we have now defined at least a few functionalities.
So again, we don't show code today.
Yeah.
Would be too much. Maybe it's a bit disappointing for you if you want to see the code of Super Mario. We don't have it now. We just want to give you a few teasers where you already need programming in like basic games and where you need the problem solving and computational thinking skills.
Exactly, yeah. But as you've mentioned, teaser.
Yeah, you teased it already a bit.
I teased it a bit.
And I'm very, very happy about that somebody in the chat already wrote this, because I wasn't sure if somebody know it. And so I want to talk a bit about phone books. And yeah, I hope at least some of you still know this kind of phone books. Back in the day, they were much larger, but you were able to find some. Most of you will use a phone nowadays, but I will show you another skill of computational thinking, which is algorithms. And one of the best things to show you that is we are looking for a person I want to give a call. So let's say I have a friend with the name Smith, so with S, and I want to know the number. Yeah, we can switch to
I
that.
think that would be beneficial, yeah.
Yeah, we can switch to that. I want to give them a call, but I don't know the number, and I'm, let's say, 30, 40 years ago. I need the telephone number. So what can I do to find the number? It's a very, very basic approach, but let's start with, I start with the first page, I start with the second page, start with the first, fourth, and so on. So I do this until I reach my colleague called Smith. Will I find him in this case? What do you think in the chat? So when I go page by page, is it here? No, it's not here. Is it here? No, it's not here. And continue this. Yes, it is correct. Is it efficient?
Exactly, yeah.
Yeah.
It would take forever.
I don't know.
Yeah.
So this is not a very huge one, but it will take me at least a few minutes to find. And this is not what we want. Okay, let's improve this a bit. Let's say I skip every second page. So take the first one, take the third one, take the fifth one, take the seventh one, take the ninth one, and so on. Is this correct? Will I find the person I want to call? Maybe, yeah, but not always. So I will have a problem when the name is between, let's like sandwiched between 2 pages. I can fix this easily because when I'm afterwards, let's say I'm at T and I know my name starts with S. Okay, then I go back one or two to go back to the name, and then I have it again. That also would work, and it would improve my first attempt by half of the time, because I would, let's say it's on page 500. In the first attempt, I would need 500 pages. In the second attempt, I would need 250, maybe 251 attempts. But this is also not how you would approach it. Of course, you can skip 10 or skip 15, but how would you approach it? How do you usually would do it? I know in the phone it's more easier with the search function, but they work pretty similar as we are searching it for now. Open in the middle, yeah, exactly. So I would just open it in the middle and now see, is it on this page? If not, okay, is it before now or after in the alphabet? In this case, I'm at K. So when I'm at K, as I know it's afterwards, so it's this part. So what we can do is,
okay,
let's throw it away.
Yeah.
We can remove this part. And then we have only the half of the phone book again. And we do it again. Start in the middle. Where are we? Oh, we are at S. Great, we are at S, but it is not the page I want to find. And we are at SA, so we are in the beginning of S. And we know it's again in the second part. So let's remove that again and throw away. So I have now 2 steps and I'm already very close to my problem. I can do this again. Look at the middle. Now I'm too far. Let's remove the right part, and I can do this once again and again, and I have now like 3 steps and I'm already very, very close to my name. So before I had 500 steps. With this short improvement I had 250 steps. And now with this algorithm I have 3 steps. Maybe let's say I'll do it 2 or 3 times more. Let's say I used 5 or 6 steps, and then I finally found my name and I can call the person. This is so much faster than just going through page by page.
Yeah, this increase of efficiency is tremendous.
Yeah, and this actually has a name. This is called binary search, and you will learn this afterwards in another lecture. There's another lecture dedicated to algorithms where you will see how you can implement this. But this was just a short teaser how algorithms work also in our daily life. I want to give you now a short representation of how this could be written, not in code directly, but in so-called pseudocode. Pseudocode is a mixture of source code and natural language, so what we are talking about. And it would be something like this. We have our target, which is the name Smith. Then, as we have done it before, look at the middle page of your current phone book. It's the first step. If the name, so Smith, was found on this page, then you are finished, then you are done. If the name was not found, choose a new search space, which means if the name is earlier in the current names, use the left side and throw the right side away. If the name is later than the current names, use the right side and throw the left side away. So you reduce your problem always by half. That's very efficient. And then in the 4th step is just go back to step 1 and look in the middle of your current phone book. If the name is found there, you are finished again. So that's basically the algorithm we are doing. And we can also write this as flowchart. As we have seen before, we start here. We look in the middle of the current phone book. Is the name on the phone book? If yes, we are done. Great job. If not, then split it up. Is the name earlier in the alphabet than the current name? If not, divide phone book and only keep right side. If yes, divide phone book and only keep left side. And in both cases, go back here and look again at the middle of the phone book. As you can see, again, an algorithm you are maybe using all the time, I'm using often. Maybe you also do it when you do not search explicitly in your phone, but just scrolling down. You just scrolling, then stop, look what name is there, and then scrolling up again or scrolling down again. It's the same principle, but it's better visible with a phone book in this case.
But we've also seen now there are different approaches to find a solution. So there are different strategies to find, in this case, the name Smith in the phone book.
Yeah,
so
that's great. A great comment. That's also one of the things you should learn. There is no one solution for a problem. There are many solutions. Some may better, some may be more better or better for a specific problem, but it depends on the problem, which algorithm you're using. In this case, for searching in a alphabetically ordered phone book, it makes sense to do it like this.
Cool to see that there are different
solutions.
That's really cool.
I brought another example of an algorithm, and hopefully some of you also know this one. It's the friendship algorithm from Big Bang Theory. Maybe you watched the episode, maybe not. It's basically, in short, it's Sheldon tried to find friends. It's hard for him, very hard. And he came up with an algorithm to get some friends. And the algorithm is something like this. He calls the person, he asks the person if he is at home. If not, leave a message, okay, wait for a callback. If yes, would you like to share a meal? So there are now a few conditions here. Wait for the response. If not, doing this. If yes, dine together. Begin friendship. Very easy. So he assumes that dining once is already a friendship, but it's Sheldon, so fair enough. If they don't want to share a meal, do enjoy a hot beverage. Okay, let's get for a drink. If not, again, now he's a bit in a trouble. If yes, you can choose for the drink. And I want to have a look now on this side here. So we have here a counter variable, n is equal to 0, and he said to the other person who wants to be friend with, tell me one of your interests, and then if Sheldon shares the interest, great, you are friends already, do this. If not, then you have to increment this n variable, this counter, and say, okay, tell me another interest, tell me another interest. And if you have more than 6 interests you're not sharing, okay, then choose the least or the best option in this case and do this.
So could we say this is a loop, some kind of loop?
This is a so-called loop, yeah. So you are, if this is always no here, then you are in a loop here, and you might be in an infinite loop. And then I think Howard is coming and adding this counter variable here to have an ending of this loop. Otherwise, it would be an infinite loop. And you don't want to have infinite loops, even in programming or also in real life. Yeah. I think it's not a good idea. But we can also, again, show this as pseudocode. So we say, okay, set n to 0, then ask for interest. If me, in this case, I'm not share the interest, then increment this n number. So let's say, okay, this n is 1. If n is smaller than 6, go to line 2 again, ask for the next interest, do this once again. If n is small, or if n is higher than 6, then choose the best interest. And if I am sharing the interest, so this here is the branch where I'm not sharing the interest, this here is the branch where I share the interest. If I share the interest, then choose this interest. this is already some kind of pseudocode we will learn in, I think, about 3 weeks, where we have these conditions with if and else. But please remember, when you then think of that, it's sometimes very easy, and it's just, in this case, like a friendship algorithm with an exit then. Were there any questions in the chat about my my phone book and this Sheldon friendship algorithm? I hope you still know Big Bang Theory. I think it's still.
I hope so. Yeah.
Yeah. Any questions from your side about the algorithms here? Hopefully you can answer them.
Would be interesting if this algorithm is applicable in the real world.
This friendship algorithm?
Friendship algorithm. Yeah.
I think you will find some people who tried this.
Yeah.
Maybe there's also a research paper about that. I don't know.
Would be quite interesting.
Yeah, would be. All right, so we have about 10 minutes left, and we have still one thing missing, which is called pattern recognition. So we had the abstraction,
we had the decomposition,
the algorithm thinking, and now we are at pattern recognition. And the first example here is, again, a question for you. Do you see any pattern here?
So you have 3, 6, 9, 12, 15 and 18. So yeah, we have it already multiple times.
Yeah.
It's either
Just
multiples of 3 or just
it's multiple of adding 3. In this case, I think
Plus
it's
3.
just adding 3 all the time. Not that hard.
yeah.
We come now again with
An
a
old
game,
school.
an old school
Yeah.
game. Just a question: who knows what this is? Anybody knows the name of this? And maybe playing this still. I don't know if it's still available.
You can play it actually on Google.
Really?
Yeah. So
I think it's, yeah. You can play it online. Yeah, of course.
yeah.
Yeah. Okay. Great. You still know it. I had very hard time to understand how it works because I was always too lazy to read the instruction.
Me too.
Just clicking around, and I died basically all the time. But it's not that hard. The game principle is there are numbers, and on each field the number indicates how many of these, I think it's bombs, right?
Yeah, it's bombs, yeah.
How many bombs are around the current cell. So in this case here is one bomb. This is this one. This one has 2 bombs. This one and another one somewhere here.
Somewhere in the neighborhood, yeah.
And your task is then to click on that and hope that it's not a bomb, because when you click on a bomb, the game is over. So this is the basic task. You have to find patterns in the numbers here and have to find out, okay, where is here a bomb? That's the basic principle of that.
Exactly. Yeah. It's your task as the playing person to really find such a pattern, to know, or at least try to know, in which of these fields could be a bomb and on which fields you could potentially click on and there's no bomb. So it's really figuring out how this could work here, for example, in Minesweeper.
Yeah. Right. I think we are already very close to our lecture for today. So just to give a short conclusion, computational thinking we talked about is to solve problems. We deliberately don't give you code to show today because we know it's hard in the first lecture to show you code, and we will learn it step by step starting with next week. But today was kind of like a motivation, a teaser, what you will hopefully acquire knowledge in the next weeks.
It's also quite overwhelming. We know that the first week of the semester, or maybe your study, so it was intentional to just illustrate it by some, we hope, fun examples or cool examples and don't show any code for now. We'll do that starting by next week.
You will see a lot of code in the upcoming week, so don't worry. And then we showed you the three parts: the abstraction, decomposition, the algorithms, and the pattern recognition. In most cases, you just need a combination of all those when you're writing code. But these are all skills you might already have. So you know abstraction, you know decomposition. It's not that hard. You know algorithms now, you use them in a daily life. But combining them in a source code program is always then a bit trickier.
Yeah.
But the basic skills are not that hard to.
Yeah, it's really about applying these skills in a computer science context. So in this case, by programming.
All right.
Okay.
This comes us to our last page for today. The main takeaways: please check our course website. Please check our FAQ section if you have questions. If you have more questions, ask on Discord. We have a lot of tutors and study assistants who are happy to help there. If you have more questions, please wait for the next lecture, next Thursday. For today, to sum it up, there is no homework or task to do. You have one more week to prepare for next week. And I think next week we will then start with the serious C programming. Life is getting serious, and we talk about data types, we talk about variables, what they are, and a bit about C, how C works. And we create our first programs. That's very interesting.
That's cool.
Yeah?
Very cool.
So very looking forward to that. Do we have left for a few more questions? I just thought of. For Design Your Own App, the lecture at Thursday is not necessary. So if you use Design Your Own App to C, yes, it's not necessary. But in general, the lecture is never necessary to go. So you have at ESP and Design Your Own App, it's up to you if you want to join. You don't have to be there. How should I prepare myself for the second assignment? I hear that maybe this person also did the second assignment last year. We know that the last year's second assignment was hard, and we then split it up into 4 assignments. So the second assignment is split into an assignment 2 and assignment 3, and it will be much easier then. In addition, doing the weekly exercises will also prepare you very good for the assignments.
Yeah, related to the weekly exercises, when will the online GDB classroom open? So actually it is open.
It is open, but there are no exercises currently available. We will publish them next week, and next week it's just about a hello world and just about a few small tasks. So as I said, no worries now. We will do it next week and publish them next week.
Yeah. Also next week, because here's the question: do you also show us how to access C, install it? So this will all be a part of the practicals.
The practicals already, yeah. So in the practicals, they will show you all you need to know to access C, to write C code, to access Git, whatever Git means now. I'll just leave it open. To show you how you can install your environment to start programming. And then in the lecture next week, we will show you how you create your own first programs.
Yeah.
All right. Anything else left?
Maybe from experience, what will be the most or one of the most complex topic we will teach?
It's a good question, and it depends a bit on your previous knowledge, but let me say that it's in the mid of November when pointers are coming. Pointers are most likely one of the, let's say, points in the semester where students struggle, but we also know that, and we try to visualize and give you as much time as possible with pointers so you can understand it. Once you understood pointers, it's not that hard anymore.
Yeah.
Trust me. And also with the weekly exercises, we will provide you small coding exercises where you can interact with pointers and work with pointers. But I would say pointers is one of the hardest things to learn.
So at least I would say it's the first really, really, really hard thing in the course.
Yeah. So until then, it's very general programming concepts which are applicable for all other programming languages. And with pointers, you are starting very C specific. Some other languages do not have pointers anymore, but C has it. And then it's getting a bit harder to understand, but it's not impossible.
No, definitely not.
Definitely not, yeah. And we try to keep it simple, and we try to take as much time as possible. So I think we have one lecture just dedicated to pointers. And when we reach this point, please also learn and practice on your own, because then definitely you can make it.
And of course, ask questions on Discord.
Yeah.
Use the personal question hours. Ask if you don't understand something. It's the best way to discuss it, and of course to try it out.
Yeah. And a great comment in the end. Pointers are awesome. We also love them. So as soon as you understand it, you think that's a pretty cool concept.
Yeah, it is.
I think we are done for today. Perfect in time. So we want to stop at 18 o'clock. Great. I also read that there's the TU Fest today.
Really?
So
That's
yeah. When it was too much for you, or when you enjoyed it, go there, have a drink. It's for you, and maybe then hopefully see you next week in the stream. Okay.
Then wish you a nice evening. I wish you a nice TU Fest.
Yeah.
Let's see us next week again.
See you. Bye.
Bye.